Hi, my name is Ava Martino, and I'll be presenting on Lab 4 of Physics 2212, Faraday's Law. In the introduction, I'll outline the purpose of the lab and introduce some key concepts used during the experiment. Next, I'll go over the details and initial conditions of the experiment. I will then analyze and interpret the computational model created on GlowScript, and finally, I'll address the what-if discussion questions. The purpose of this lab is to observe data of a falling bar magnet through an aluminum tube and compare it to a computational model. In this experiment, the system is the bar magnet and aluminum tube, while the surroundings constitute everything else. For a preview of the results, the average fall time through the aluminum tube was about 0.31 seconds in the experiment and about 0.34 seconds in the computer model. Some key concepts used during the experiment are Faraday's law, which describes how a changing magnetic field can induce an EMF or voltage in a circuit. The equation is EMF is equal to the change in flux over time. The Biot-Savart law, which is a fundamental equation in electromagnetism that describes the magnetic field generated by a constant electric current. We also use Newton's second and third laws. And finally, Ohm's law, which describes the relationship between voltage, current, and resistance in an electrical circuit, which you can see at the bottom. So starting off with the procedure for our experiment, we had to record the bar magnet falling through an aluminum tube with the north side up. We then need to find the time it took for the magnet to fall through. I repeated this 5 times and found the average time to be about 0.31 seconds. Here is my experimental data. Before we move on to the coding part of the lab, I measured the length and width of my tube, which was about 0.3 meters and 0.005 meters. I also recorded the inner and outer radius, which was 0.0254 meters and 0.0304 meters. Finally, I found the weight of the bar magnet to be about 0.027 kilograms, and the dipole was 2.525 amperes times meters squared. Here's my GlowScript code. In step 1, I just inserted the magnet's mass and dipole. Then for step 2, I created the magnetic field using the magnetic field equations. In step 3, I created the magnetic force using the magnetic force equation and Faraday's law. And then for step 7, I added the force of gravity on the magnet. So now going back to step 4, I coded the current in the ring using Faraday's law. And for steps 5 and 6, I coded the magnetic fields for each of the rings. Lastly, for step 8, I utilized Newton's second and third laws to update the position and velocity of the bar magnet as it travels down the aluminum tube. Here are my results. In the graph, you can see a curvature in the velocity created by the magnetic fields, causing the magnet to have a slight break as it falls. The final time in seconds that it took for the magnet to fall according to the computational model was 0.347 seconds. Initially, the dipole for my magnet gave me an answer that was about 0.5 seconds off from the time that I found. So I recalculated the magnet's dipole and was able to reach a number that was much closer. Now, to interpret the simulation, the blue color indicated the clockwise rotation created by the induced current to counteract the magnetic flux from the bar magnet. This is known as Lenz's law. Nature abhors a change in flux. The red was the counterclockwise rotation from the bar magnet falling downwards. What happens to the dynamics of the system when you flip the magnet around? If you flip the magnet the other way, there may be slight differences, but the dynamics remain the same. How might the computational model be made more accurate? The computational model could be made more accurate if it had taken into account air resistance or other forces that may have not been accounted for. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The shape of the velocity versus time plot tells us that the bar magnet was braking as it was moving through the aluminum tube. If it had a constant velocity, such as in free fall, the slope would be linear. Some errors that may have occurred are inaccurate timing of the magnet as it fell through the tube and air resistance or other forces that may have not been considered. Now moving on to the discussion questions. What if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? The magnet's velocity would decrease because of the increase in induced current and magnetic force that would cause the braking to increase. Now, what if holes or slots were cut into the tube? How would this affect the rings in your model? The rings wouldn't be even, so some of the currents in the rings would be stronger or weaker than in others. This would cause the magnet to have a slightly faster velocity.